paper I will talk about is the joint paper with my colleague Pedro Torres from the University of Granada in Spain. In the shallow water theory, the motion of small amplitude waves are described by these two partial differential equations, where eta is a vertical water surface elevation. Maybe it will be better to look at this picture. So eta is a vertical surface elevation. U is a depth average water flow velocity. It is not here, but H is a perturbed water depth. And G is a gravity acceleration. And without loss of generality, we will assume that this G is equal to 1. These two partial differential equations can be decoupled in the following way. Either we take the partial derivative according to t from the second equation and use the first equation to get the equation 2, where only the water flow velocity appears in this equation. Or we can derive the first equation according to t and use the second to get the equation 3, where appears only the surface elevation. And we will focus on these two decoupled equations, 2 and 3. So a traveling wave is a special solution of this form, where this q is known as amplitude of the wave, omega is a frequency, and psi is the phase. And usually the question is if we know the h, so if there exists solution u, respectively eta. But this inverse problem is that if we have a prescribed amplitude q, can we determine a suitable function h such that this traveling wave with this prescribed amplitude is a solution to this particular equation? We start with the equation 2, and we will see that it is resolved already, and we then pass to the equation 3, and this will be much more interesting. So as for the equation 2, we know the C plus T as a space of continuous t-periodic functions with positive values. And we are interested in if there exists a solution to the equation 2 for prescribed function q that is also t-periodic. And so we take the solution of this form, and this is of course complex function, so we put it in the equation 2. We derive according to t, according to x. We separate the real and imaginary parts. This is the real part is equal to 0 and imaginary part equals to 0. The equation 5 means that certain conserved quantity is hq in the power of 2 psi prime. This is conserved quantity because this derivative is equal to 0. This follows from the equation 5, and therefore we can denote it by some alpha. This is a constant, and if we use this the relation 6 in the equation 4, we get the second order ordinary differential equation of this form. This is the second order ordinary differential equation with the space singularity. And this problem has already been tackle with a lot of mathematicians, and this particular case can be resolved using the paper of Laser and Solimini from the 1987. So for this equation, there always exists a solution H that is positive periodic, T-periodic. The only condition is that alpha and omega are different from zero. So this is the problem about the water flow velocity, and we pass to the problem of surface elevation equation. Pardon. We start with the same thing as before. The equation 3 we suppose that the equation 3 has a solution of this form, of the traveling wave form. And we put it in the equation 3, we derive and separate real and imaginary part, obtaining the equations 8 and 9. Again, the equation 9 means that some quantity again is conserved. So we denote it by alpha and use it in the equation 8, and we get another differential equation of the second order of this form. And this looks similar to the previous one, but it differs because here the derivative is according this is the derivative of q, and then it is derived as a multiplication. And this exactly is the problem, because we suppose that q is a t-periodic function. Unless q is positive, but the derivative of q, of course, change its sign. So also has zeros at some point. Somewhere it is positive, somewhere it is negative. So this term causes a lot of problems with investigation of this differential equation. One of the way how to tackle with this problem is to divide the whole interval 0t into some subintervals a, b, where the q prime is of the constant sign, or is positive, either is positive or is negative. Resolve the problem on every subinterval, and then glue the solutions to the solution of the original equation on the whole interval. But to do this, we need to know, of course, the limits of the solutions on every subinterval and other behaviors of this solution. So we divide the interval 0t to the subintervals a, b, such that at the endpoints, the derivative of q is 0, and inside the interval AB, q prime is of constant sign. Then we take this substitution, and the substitution transform the equation 10 to the equation 12. Here, lambda is fraction alpha over omega square. This alpha omega is in this lambda. And so we will investigate the equation 12, and we will start with the subinterval AB, where the q prime is positive. We assume that the second derivative at the point A is positive, and second derivative at the point B is negative. So the equation 12 gets the form 15, and for the technical reasons, we embed this equation 15 to the system of to the equation 16, where we use also this signum. This is just technical reason. It has no influence on this. So you can see that the non-negative solutions of 15 and 16 are the same. So we, because if we are go back to this transformation 11, we are interested in the, we have prescribed Q and we are interested in the function H. So if we are looking for the solution H that is positive, then because Q prime at the endpoints is 0, necessarily U also has to be 0 at the endpoints. Yes, and then some limit must be calculated also. That is why we look for the equation for the solution to the equation 16. By the solution of 16, we understand the function that is C1 and satisfies the equation 16 for every x from the interval AB, and is subject to the initial condition UA at the point U at the point A is equal to 0. So we have this differential equation with the boundary condition, and this the existence of the solution, there is no problem with the existence, because this is the initial problem for the first order equation, where on the right hand side is a sublinear function. So the existence is guaranteed. There always exists a solution on the whole interval, and but we need to investigate other things also. We are interested in the cases when the solution U at the point B is also 0. Of course, this can be done by this parameter lambda. Then we need to prove that there exist one-sided limits of this form, and to find what the values L sub A and L sub B are equal to. Pardon. Because then, as U is defined by this way, then H we get using this relation. So that is why we need the limits at the points, the one-sided limits at the points A and at the points B of these fractions. And the following, there exists a threshold lambda sub AB such that if lambda is below this threshold, then the solution at the point B, then the solution U is positive, is at the point B, it is equal to 0. There exist one-sided limits L sub A and L sub B, and these values are roots of certain, are positive roots of certain second polynomials, quadratic equation. And if lambda is greater than this critical value, then U at the point B is positive. So that means that the function H on this subinterval at the point B tends to plus infinity, and so it doesn't require it doesn't meet our requirements on the continuity of H on the whole interval. The sketch of proof to this theorem is that the base is we show theorem on differential inequalities. So if functions u sub 1 and u sub 2 satisfies these differential inequalities, so u sub 1 prime is less or equal something, and u 2 prime is greater, with different parameters lambda 1 and lambda 2, then if u sub 1 at the point A is less than u sub 2 at the point A, and the parameters lambda 1 is less than parameter lambda 2, then also this function u sub 1 and u sub 2 are related with this. U sub 1 is less than u sub 2 on the whole interval. This, of course, means that if the function u sub 2 at point B is 0, then necessarily u sub 1 also at the point B is equal to 0. And on the contrary, if u sub 1 at the point B is positive, then u sub 2 at the point B is also positive. This, of course, shows that there exists some critical point, but it is necessary to show that for sufficiently small lambda 1, there exists a solution that meets 0 at the point B. And this can be done in this way. If lambda is sufficiently small, then there exists a positive root of this quadratic equation. And from here, q sub 0, this is the minimum of the second derivative of the function q. And because q prime is positive, so q is increasing in the interval AB. So from this quadratic equation, we get this inequality. And this inequality also we get if we define u sub 2 by this way. This inequality means that u sub 2 defined by this way satisfies this second order, this differential inequality. And therefore, we have constructed, you can see that u sub 2 at the point A, also at the point B is 0, and therefore solution to this equation 16 must be below u2 according to this theorem on differential inequalities, and it is positive, and so necessarily the solution must be 0 at the point B also. On the other hand, if lambda is sufficiently large, then u sub 2 and B must be positive. This is because if we have to show that if ub is 0, then there exists finite limit LB, and this finite limit is a root of this quadratic equation. But if lambda is sufficiently large, this quadratic equation has no real roots, and therefore there cannot be this finite limit. So u of B cannot be equal to 0, must be positive. This follows. So we have for small parameter lambda, the solutions are at the point B are equal to 0. For sufficiently large parameters lambda, the solutions at the point B are positive. So there must exist a threshold lambda sub 0, or say lambda AB that divides these two sets of parameters. Yes. Now, if we pass to the interval where the q prime is negative, then simple substitution q tilde is equal to q of minus x. Transform this case to the previous one because q tilde prime is positive. Yes. So this substitution transforms this case with negative derivative of q to the previous one where the derivative is positive. And so we can formulate our main result, and that is if q is sufficiently smooth, so of the class C2, there are critical points are non-degenerate. That means that if q prime at the point x equals 0, then the second derivative is different from 0. Then there exists a threshold lambda sub 0, such that if this fraction is less than this critical value, then there exists a positive t-periodic solution of 10, and on the contrary, if it is greater, then there is no positive solution, t-periodic positive solution. This lambda 0 is the minimum of all these thresholds lambda AB, for where lambda AB is corresponding critical value for this subinterval AB. So we take the minimum of all this lambda AB. Here we have some estimate also for this lambda sub 0 for this threshold, but this estimates is very wide, and to get this estimate much more narrow, we can use this theorem about these differential inequalities. Again, if we are able to construct some periodic functions, not exactly periodic, but functions that are absolutely continuous, satisfying these differential inequalities with corresponding parameters lambda 1 and lambda 2, and some condition, it must satisfy some conditions, then we can conclude that this critical value lambda AB that corresponds to the interval AB is between this parameter lambda 1 and lambda 2. If we take the functions v and w in this particular form, then the previous theorem can be, or differential inequalities can be rewritten in this form. And if, for example, the functions the functions L1, L2 are constant functions, so this prime is 0, this is 0, this is 0, so you get some second order quadratic roots to check. So finally, I will show you how to apply this result for a simple example. So we will assume that the function q is 2 minus cosine x, and the whole interval is 0 to p, and this can be divided into two subintervals, 0p and p to p, and on every interval we have the derivative of q is positive on the first interval and negative on the second interval. And you can see that according to the symmetricity, it is very symmetric function. So you can expect, and it is that the thresholds on the subintervals are equal, and therefore also the threshold on the whole interval is equal to this threshold on the subinterval. So it is sufficient to find one threshold or estimate one threshold on the interval 0p, for example. If we use the estimate of the main result, we get a very large region, 0.25 from below, and from above it is 60.75. This very large. So we can use the corollary and, for example, start with the constant functions L1 and L2. Then if we define lambda 1 in this way, lambda 2 in this way, we get that critical lambda is between these two. So if lambda 1 is lambda 2 is equal to 3/2, then we get 3.75, and the above doesn't change. It's still too wide, this estimation. So if we analyze in more details these mappings, then we can obtain optimal values when functions L1 and L2 are constant. And we get the estimate 11.02, and from above it is something like 48.82. Yes, this is better, but still it is a quite large interval. So we have to look for some suitable test functions among the non-constant functions. So if we define L sub 1 and L sub 2 in this way, for example, with these coefficients, and we have to also verify that other assumptions of the corollary or theorem 3 are satisfied. Finally, we get the estimate of this critical value like 26.4, 21.68. This is better than the previous, of course, better than the previous estimates. And for this particular case, if we look at the function h, so if we change parameter lambda is 1, lambda 2, 3, 4, 5, and the root of 27. So you can see how the solution h change according to the change of parameter lambda. Lambda critical is somewhere 29, lambda square is 21, 29 or 30. So that's all, and thank you for your attention.